Okay, hello everyone, and welcome to this week's SNAC seminar. I'm very pleased to welcome Yuanzhao Zhang from the Santa Fe Institute, who's been kind enough to join us and speak this week. So Yuanzhao is a Schmidt Science Postdoc Fellow at the Santa Fe Institute in New Mexico, a wonderful institute, the spiritual home of complex systems. Several of us here have visited there in the past. I was there for a summer school many years ago, which was wonderful. So I can only imagine it's an amazing experience to be a postdoc there and interacting with so many interesting people. To further the introduction for Yuanzhao, he's working with Stephen Strogatz at Santa Fe and also spent a year with Stephen at Cornell beforehand. Again, Stephen is a towering figure in complex systems, so that must be a wonderful connection to have. Yuanzhao's PhD was in 2020 in physics from Northwestern University, working with Adelson Motta. Yuanzhao works at the interface of networks and nonlinear dynamics. I thought it was very interesting that your Twitter bio says not too nonlinear systems, which is obviously the key when we're working with these systems and trying to get some analytic insights. Yuanzhao looks at the intersection and the relationships between structure, dynamics, and function, which is one of our key interests here in the SNAC seminars, and is obviously why we've gotten him to come along and speak today. A particular focus of his is on synchronization, and the title of today's talk is going to be Designing Temporal Networks that Synchronize Under Resource Constraints. So it's wonderful to have you, Yuanzhao, and I'll throw over to you now.
Thank you, Joe, for the kind introduction. So as Joe said, my background is in nonlinear dynamics and complex systems in general. So I have to say I'm an amateur in neuroscience. So I would love to also learn from you guys today. So please do feel free to interrupt if you have any questions or comments. So my topic today will be talking a little bit about temporal networks and synchronization. So first, what is synchronization? To put it simply, it's basically everyone doing the same thing at the same time. So you can see clearly that people in the left picture is not synchronized, and those in the right are considered synchronized. So why should we care about synchronization? To me, synchronization is an important mechanism through which microscopic entities can achieve a macroscopic impact. For example, our circadian rhythm is produced by about 20,000 neurons inside a small region of our brain called suprachiasmatic nucleus. So you can imagine that any one of those neurons will not be able to make any meaningful impact on our circadian rhythm. So what they do is that they synchronize with each other to produce a macroscopic oscillation of protein and chemical concentrations, which in turn gives rise to our robust 24-hour circadian rhythm. Lots of the neuronal dynamics in our brain are much more complex than the full synchronization I just showed. For example, there can be some very intricate synchronization patterns that goes on in the brain. For example, a recent study shows that by using external stimuli that coax the two red regions of the brain into remote synchronization, we can actually improve the short-term memory of older adults. So there's a strong connection between the dynamical patterns of the neuronal populations in our brain and the functions of our brain. And those patterns are not only important for brains that are awake, they're also important for brains that are asleep. So one example comes from dolphins. So dolphins, they do not sleep in a naive way like we do. They only have half of their brain asleep at a time, while the other half stays awake. So this allows dolphins to keep swimming and stay alert while sleeping. And in terms of the neuronal dynamics, the sleeping half of the brain has dynamics that are highly synchronized, while the non-sleeping half of the brain, the dynamics is highly incoherent. So this is what people usually call the chimera states, which describes the coexistence of coherence and incoherence in a single system. And moreover, the sleeping and non-sleeping half of the brain, they actually switch roles every 10 to 20 minutes so that both sides of the brain can get rested. Now, synchronization is not only appear for regular brain functions, they also appear for pathological states in the brain. For example, seizures, they are characterized by locally synchronized neuronal dynamics that are embedded in incoherent neuronal populations. And there are actually some very interesting features about seizure dynamics. For example, although seizures are linked to the increased synchronization level in the brain, right at the onset of the seizure, synchronization actually often decreases before it goes up to initiate the seizure dynamics. And then right before the seizure termination, the synchronization actually often increases to a very high level before dying down and signaling the termination of the seizure. Okay, so that's a little bit background on synchronization. Let's talk a little bit about temporal networks. So people use temporal networks to describe complex systems whose interaction patterns change over time. You know, one example would be the connections between neurons in our brain, you know, they change all the time. And one fundamental question that we can ask about temporal networks is that what are the dynamical consequences of the temporal variations in the network structure? Specifically, I will be focusing on the synchronization dynamics on temporal networks. And we're interested in whether temporal networks can synchronize better than static networks. And the answer is a resounding yes. But there are some nuances here. And actually, it is yes for a few different scenarios. First is that temporal networks can synchronize better than their time-frozen counterparts. What I mean by time-frozen counterparts is that if you consider this entire time series of the networks as a temporal network, then at each time instant, it would have a different configuration, and each of those configuration would be considered a time-frozen counterpart of the temporal network. And one example in which the temporal network synchronizes better than those time-frozen counterparts is that imagine at each time instant, if your configuration is a disconnected network, so obviously that will not synchronize. But if you switch between those disconnected configurations fast enough, then on average, your temporal network would synchronize because over time, all the nodes would be connected for some time interval, which can lead to synchronization. Another scenario would be comparing the temporal network to their time averaged counterparts. What that means is that you take all those network instances and you combine them into a single time averaged static network, and you compare that with the temporal network. And it has been shown that temporal network can often outperform their time averaged counterparts. But then here is the ultimate question, which no one has asked before. So are there temporal networks that synchronize better than all possible static networks? So imagine the universe of any static network that you can come up with. Can we find temporal networks that synchronize better than any of those static networks? So the answer is no, if we constrain the temporal networks to the fast switching limit, meaning it is switching between different network configurations extremely fast. The reason is that in this case, people have shown that the fast switching temporal network actually has an equivalent representation using their time average static counterpart. So they can be reduced to a static network, which obviously cannot do better than all possible static networks. So then the question is, how do we compare a temporal network against all possible static networks? Obviously, we cannot say do the comparison one by one because there are infinitely many static networks. So what do we do? First is that we want to limit the total coupling budget, meaning we want to put a limit on the resources available to either the static network or the temporal network, so we can make a fair comparison. Second is that if we can find a fundamental limit for synchronization in static networks, meaning if we can find the static networks that are optimal for the purpose of synchronization, then we can just simply compare our temporal networks to those optimal static networks, which would make the comparison more feasible. So, okay, so first, what do I mean when I say imposing a finite coupling budget on a network? For that, we need to define what we call the graph Laplacian, because we assume all the couplings in our network are diffusive. So this graph Laplacian is defined in terms of the adjacency matrix, which I assume most of you should be familiar with. So here, Aij is one entry in the adjacency matrix, and it encodes the edge weight from node J to node I. So when we say we have a finite coupling budget, what we mean exactly is that we constrain the sum of all entries in the adjacency matrix A to be n-1, where n is the size of our network. So if we translate this condition to the graph Laplacian, what that means is that if we sum over all the diagonal entries in the graph Laplacian, it is easy to see that this sum is actually equal to the sum of all entries of the adjacency matrix A. So this sum should be equal to n-1 as well. And we know that the sum of the eigenvalues should be equal to the trace of the matrix, which is basically the sum of the diagonal entries in our graph Laplacian. So basically, our finite coupling budget condition gets translated to the sum of all the non-zero Laplacian eigenvalues being n-1. And I shall mention that because the way the graph Laplacian is defined, it always has a trivial eigenvalue λ1 that is always equal to 0. So here we are just doing the sum from I equal to 2 to I equal to n. So then, what are the optimal static networks? In this case, the optimal static networks are those networks that has a fully degenerate non-zero Laplacian eigenvalues. So remember, we have a constraint that summing over λ2 to λn should equal to n-1. So if we assume all the non-zero eigenvalues to be equal, then all of them should be equal to 1. So this would be the condition for optimal static networks under our finite coupling budget constraint. And here are some examples of optimal static networks for 6 nodes. So you can see some examples include a direct chain network, also includes the complete graph, which we will use later. So now, why do we say those networks with fully degenerate eigenspectrum are optimal static networks for synchronization purpose? So to understand that, we need to use a formalism called the master stability functions formalism. So we start by considering a generic model of a network of coupled oscillators. So here xi represents the state of the ith oscillator, and the function f describes the dynamics of the oscillator, and the sigma is the coupling strength. The coupling for the coupling matrix, we use the graph Laplacian L, and H is the interaction function that tells us how the node J sends information to node I. So if we want to analyze the stability of a fully synchronized state, which is x1 equal to x2 equal to xn for all time t, then what we need to do is we need to linearize the system around the synchronization trajectory, and we will get this so-called variational equation where delta x basically represents the perturbation we apply to the synchronization state. And by evolving this equation, if the perturbation delta x grows over time, then we know the synchronization state is unstable. If it decays over time to 0, then we know the synchronization state is stable. So here's a more visual representation of the variational equation here. So you can see that there are two matrices in the equation. The first one is the identity matrix, and the second one is the Laplacian coupling matrix. So because of this coupling matrix here, the dimension of our equation grows with network size. So you can imagine that when the network is large, it'd be difficult to analyze this, this variational equation for our stability analysis. So that's why Temporal and Carl introduced these new coordinates about 2 decades ago. And so the basic idea is that, okay, so why don't we just find a new coordinates that diagonalize the coupling matrix L? Then this would give us a new set of equations under these new coordinates that are fully decoupled, meaning there are n decoupled variational equations under these new coordinates. And we can analyze each of them independently. So mathematically, so it's very similar to the classical model analysis we all learned in classical physics. So basically, you have a high dimensional variational equation, and we decouple them into low dimensional ones. And the interesting thing is that where eta I represents a perturbation mode that evolves independently from all other perturbation modes. And so what's interesting is that for all those perturbation modes, the equation all have the same form, and the only difference is the value of this Laplacian eigenvalue lambda I. So what people usually do is they set the product of the coupling strength sigma and the eigenvalue lambda to be alpha, and they let this alpha to be a free variable. So for each fixed alpha, we can calculate the Lyapunov exponent of this decoupled equation. And we can plot the maximum Lyapunov exponent as a function of this free variable alpha. So now if the Lyapunov exponent is positive, then we know the corresponding equation is unstable. And if the Lyapunov exponent is negative, then we know it corresponds to a stable solution. So then we can divide the space into the stable region and the unstable region. And this is fully determined by the local dynamics F and H. And now this allows us to separate the local dynamics from the network structure. And for any given network structure, we can simply calculate the non-zero Laplacian eigenvalues and project them onto this complex plane. If all those eigenvalues are inside the stable region, then we know the synchronization state is stable. Otherwise, we know it's unstable. And from this picture, it should be clear why we define our optimal static network to be the networks that have fully degenerate eigenspectrum, because we want all those eigenvalues to be close to each other, as close as possible. This way, it would allow us to fit them all into the stable region at once. Otherwise, if they are spread out, then by fitting one eigenvalue inside the stable region, you could inevitably put the other eigenvalues outside the stable region, making the synchronization unstable. So that's the rationale behind the definition of the optimal static networks. Okay, finally, a little bit formalism is that when we go from static networks to temporal networks, things become more complicated. specifically the coupling matrix L, now it's a time-dependent matrix. And it is usually not possible to diagonalize this time-dependent matrix for all time t. So here for analytical simplicity, we focus on temporal networks whose graph Laplacian L commute for all time t. And this might seem to be a huge constraint. But what we can show with that is that even within these restricted subclasses of temporal networks, our design temporal networks can already outperform all possible static networks. Now, then the question is, what's the intuition? Like, when can we expect temporal networks to outperform static networks? So it turns out the master stability function is a very informative tool for this purpose. So again, just a reminder, the master stability function lambda of alpha is basically the Lyapunov exponent. It's a maximum Lyapunov exponent for this decoupled variational equation. And what we want to focus on is the first zero of the master stability function here. So what happens is that basically a positive master stability function means instability, and the negative region means stability. So recall that for our optimal static networks, all the non-zero eigenvalues equal to 1. So this first zero, alpha zero, actually coincides the critical coupling strength sigma c that you need to make the network synchronize stably. So what the temporal network can do for us is that instead of fixing the eigenvalue at 1, it allows the eigenvalue to change over time. So you can imagine that it oscillates around the first zero. And when it goes past the first zero, it gains stability. And when it goes below first zero, it loses stability. So if we can gain more stability by going in this region for part of the time, that outweighs the stability we lose in the unstable region, then we can expect our temporal networks to outperform even the optimal static networks. So this tells us that the curvature of the master stability function at its first zero would be a key indicator for the performance of temporal networks, especially if its second derivative is negative, meaning its curvature is negative, then we can expect the temporal networks to outperform static networks. So this inspired us to have a simple design for our temporal networks. So we start by designing the time evolution of our Laplacian spectrum. So what we do is that we separate the eigenvalues into two groups that oscillate in different directions. So when one group goes above 1, the other group goes below 1, and they do this back and forth. And we designed it in such a way that the sum of all the eigenvalues at any given time t would always equal to n minus 1. So they always satisfy the resource constraints. Here, the parameter A basically measures the amplitude of the oscillation. So what we call the temporal activity, and omega is the switching rate, basically how fast is the oscillation of our eigenvalues. Now that we have the eigenvalues, all we need to do is just to choose a set of orthogonal eigenvectors, which when combined with eigenvalues would give us the time evolution of our temporal networks. And we have a lot of freedom in choosing our eigenvectors. So here's just one example that we get from a specific choice of eigenvectors. So this kind of illustrates the time evolution of our network. The orange part is the edges that get strengthened. So there's more weights on those orange on these orange edges, and the blue ones are thinner and have less weights. So basically you can see that the resources kind of goes back and forth between different parts of the network. So at this time instance, this part of the network is getting strengthened, and then the resources flows back to the rest of the edges. And so you have this back and forth borrowing and returning of the resources. So intuitively, why it works is that basically some of the perturbation modes borrow resources from the other perturbation modes in order to remain stable, and then they return the favor at a later time, so that the other modes they borrow from can also remain stable. So one interesting thing about this design is that it is open loop, meaning that it is not an adaptive network. So the evolution of the network structure is decoupled from the state of the nodes. And also it's pretty versatile. We don't care like what are the details of the node dynamics. As long as the master stable function has this negative curvature at its first zero, the design should work and improve synchronization regardless of the details of the node dynamics. So in order to see this in action, let's just consider a simple model of Stewart-Landau oscillators. So this is the equation describing a network of coupled Stewart-Landau oscillators. It doesn't matter, the details doesn't matter. So basically, the network would admit a synchronized state with limit cycle oscillations. And it's the normal form of the dynamics for any system that emerge from a Hopf bifurcation. So the first thing we did is we plotted the master stability function for the Stewart-Landau oscillators. And you can see that there's this negative curvature at its first zero. So this gives us confidence that our designed temporal network should perform better than all possible static networks. And this is exactly what is being shown on panel B, where we plotted the stability, which you can just think of as the Lyapunov exponent. So positive means unstable and negative means stable. So we plotted this quantity for different combinations of the temporal activity A and the switching rate omega. So here's a green line, which corresponds to zero temporal activity, actually corresponds to the optimal static network, which is above zero, so unstable. And you can see that our temporal network consistently outperforms the optimal static network by becoming more stable. And there are two interesting limits that I want to point out. The first is the slow switching limit, where the switching rate omega approaches zero. So basically, this is a case where the network structure changes very, very slowly, and the switching period is effectively infinite. So in this case, we can actually theoretically predict the stability of our temporal network, which are shown as those dashed lines. And these are obtained basically by averaging the master stability function around its first zero. So averaged over a finite interval where the eigenvalues traverse between. Then there is the other limit, the fast switching limit, where everything is changing so fast that the omega goes to infinite. So in this case, we can see that they all converge to the value that is the optimal static network. And what happens here is that our temporal network has the same stability as its time averaged counterpart, which in this case happens to be a complete graph, which is a case of the optimal static networks. So it looks like that our stability is being optimized at the slow switching limit, but in practice, it is not ideal to make your switching rate too slow, because then your network would already lost the synchrony long before any meaningful change can occur in a network. So as a consequence, we don't have stable synchronization in the slow switching limit, and we don't have improved synchronization in the fast switching limit. So what happens is that very often our temporal network performs best at some intermediate switching rate. So here are some direct simulations. So basically there are 3 panels. The first panel corresponds to slow switching. The middle panel corresponds to systems with intermediate switching rate, and the third panel corresponds to systems with very fast switching rate. So here xi would be the states of the different oscillators. Delta measures the difference between all the oscillators. So a small delta means the system is highly synchronized, and a high delta means the system is desynchronized. So you can see that for slow switching, the system becomes desynchronized over time. And for intermediate switching, the system remains fully synchronized, and the difference between the oscillators actually goes down over time. But as the switching becomes too fast, then we lost synchronization again. So okay, up until now, I have focused on time continuous systems that are described by ordinary differential equations. So, but actually our design also works for systems with discrete time dynamics. So for example, those are those described by discrete maps, such as logistic maps, things like that. So here's just a very simple models that are analogous to the one which we have just seen. Here again, xi represents the ith oscillator at time t+1, and beta times f would be the intrinsic dynamics of our discrete time oscillator. Sigma is the coupling strength. The Laplacian, the graph Laplacian describes the coupling between the oscillators, and we use the same function f for the interaction. And here we assume the f is from the a map from the real number to a real number. Again, we can write down the decoupled rational equations in a very similar form. The details doesn't matter. What turns out is that in this case, we can write down a very simple form for the master stability function, which is basically a log function plus a constant. And this constant is determined by the dynamics f. Now here's the fun part. When I said that the temporal networks can synchronize better when the curvature of the master stability function at its first zero is negative, then you might imagine, okay, then probably it works for half of the system and doesn't work for the other half. But turns out that if we take the second derivative of this master stability function, it is always negative, meaning our condition for improved synchronization in temporal networks is universally satisfied for this class of low-dimensional discrete maps. And we can very easily adapt our design for time continuous system to time discrete system. So basically, we can switch between those two configurations every t steps. And we have a very simple formula for the stability of this temporal network, which we plotted here. Then we can do a bunch of simulations to numerically calculate the stability for different switching period t. Here for visibility, I shifted each curve vertically slightly. So without the shift, you can see that all of them collapse onto a single curve. What it means is that the stability of our temporal networks in this case does not depend on the switching period t. So So our improvement on synchronization actually works for any switching period here. And to see the improvement, you can just see that our stability gradually improves as we increase the temporal activity A. And those curves are obtained by using a model for the optoelectronic oscillators, but it also works for any other mapping function f as long as it is low dimensional. So you can just pick any your favorite discrete model of neurons, and the same result would hold.
Yuanzhao, can I just jump in? There's a question on the chat on the previous slide. So James Henderson is asking, do the oscillators synchronize with the switching of connections, or are there some other interesting relationships between synchronous activity and switching activity?
Let me just do the oscillator synchronize with the switching of connections. Yes. Are there any other interesting relationships between synchronous activity and switching activity? Yes. So so synchronization. When we talk about synchronization, it's between the nodes, and here we control the switching behavior of the network structure. And basically, by switching those network structure in an appropriate way, we can stabilize the synchronization between the nodes. So I'm not sure whether that's a question that's being asked, but that's kind of a relation between the switching between networks and the switching and the synchronization of the oscillators.
James, feel free to jump in if you need a clarification, or is that okay?
Yeah, I was just wondering if, because you have some kind of synchronous activity in the nodes themselves, if that synchronous activity is dependent upon or related to actually the switching activity. So if you change.
I see. So you're asking whether the synchronized dynamics would be affected by the switching of the networks. Is that
Yeah.
Right. Okay. So I didn't go into too much details, but here the answer is no, because we assume the coupling is to be diffusive, meaning when the two nodes, when they have the same state, then the interaction between them vanishes. But in general, yes. So if your networks are not diffusively coupled, then the change in the network structure will definitely change the dynamics of your synchronized state.
Okay, thank you.
Right. Okay. So here's just a brief summary of what we just discussed. First, we show that temporal networks can synchronize more efficiently than any possible static networks. And we show that time scales matter unless your node dynamics is discrete and low dimensional. Also, the interesting thing is that the same design can be applied to very different systems, meaning it is not sensitive to details of the node dynamics. For example, we show that the same design works for both stereo oscillators and for optoelectronic oscillators, and potentially many other different models. Also, we have quite some flexibility when we design those networks, because each different choice of our eigenvectors would give rise to a different realization of temporal networks. All of them would synchronize more efficiently than static networks. But if you look at the evolution of each individual edges, then they would look very different across different realizations. Finally, I didn't show this explicitly, but we did some numerical simulations, and it turns out that our design our implementation of the temporal networks doesn't have to be perfect. There can be some noise. You can have some fluctuations, some imprecisions in your network structure, and it will still improve synchronization. Some interesting future directions. For example, here we focused on commutative temporal networks for technical reasons. But what about non-commutative temporal networks? Can they improve synchronization even further, especially for random fluctuations? Those random fluctuations, they often make the temporal networks non-commutative. So can those fluctuations, in some cases, outperform our design temporal networks? And finally, we have a notion of optimal static networks for the purpose of synchronization. Can we find optimal temporal networks for this purpose as well? And on the application side, can we apply those simple designs to real-world systems, such as robot swarms or even neuronal populations? But obviously, I'm not an expert in this area, so I'll be very interested to hear your opinions on this. Finally, let me just thank my collaborator, Steve, and yeah, happy to take any questions.